Okay, it looks like it's time for the webinar to start. Just wanted to thank everyone for dialing in today. And just to introduce myself, my name is Kyle Barron. I'll be presenting the study group webinar today. I'm a senior scientist at Metron Research Group. And today I'm going to be giving you just a brief overview of mrgsolve, which is an R package that we maintain that we use to simulate from PKPD and systems pharmacology type models. So models that are written in systems of ordinary differential equations. VJ asked me to remind you today that you can, if you want to ask a question, you can do it during the webinar and do it on this discuss group, the ISOP discuss group. There's a thread for the presentation here. And I also wanted to, well, yeah, so you can post it here. I'll try and look in maybe toward the end of the webinar and see if I can take some of the questions as they come up, or anyone else that wants to respond to create the discussion on the ISOP group. Please feel free to do it here. Okay, let's get started. So just a couple of slides just to do a brief introduction, just to orient us for today. We've got several very robust and really fast packages now available for simulating from ODE-based models in R. So Ron Kaiser did a presentation a couple weeks ago on PKPD Sim. We've got RxODE, and I think the Licksoft has the MLXR package. So there's lots of options that are available. It seems like these kind of sprung up, and obviously there's just a huge need for this kind of to be able to simulate from these types of models for pharmacometric applications in R. Today I'll be telling you about mrgsolve. We've been developing that since about 2011. And we originally got into this space because we needed to support a large quantitative systems pharmacology model. It was in Berkeley, Madonna at the time, and it was just getting too big, and we needed some more flexibility and some more just performance. So we ported that model into Dissolve, which is another R package for doing differential equations, and we kind of built this R front end to Dissolve. And so the model stayed in that kind of environment for a while, and then somewhere around 2014, we said, well, we want to take more control over how the model gets kind of curated and run, and so we went and we grabbed this ODE pack and grabbed a Fortran solver out of that. We started building a simulation engine written in C++ and RCPP, and started kind of expanding this package a little bit. And so now at Metron, at least, this is what we do. This is what we use for all of our systems pharmacology modeling, and I think the package has gotten robust enough that we use it for just day-to-day work when we're working with traditional population PKPD type models. So anything from backing shiny apps to simulation-based diagnostics to predictions for dose selection and things like that. So it's kind of part of our everyday workflow at Metron now. mrgsolve has been public release since fall 2015, and it's now available on GitHub. So all the code is maintained up there, and we're trying to promote kind of community development of the package within the pharmacometrics community. So why mrgsolve? Or actually, I want to go. Well, yeah. So why would we make a package like this? Why mrgsolve, or why PKPD Sim? And Ron talked about it made a couple points a couple weeks ago. I mean, there's just such a convenience factor for being able to do these simulations from R without having to leave R. These simulations tend to be fast, so your model gets compiled in C++, and we can pass our objects into the simulation and receive output from the simulation, and they all stay in R. They stay in your memory, so we generally never need to write any data to a file. So that saves a lot of performance. And we've really tried to customize mrgsolve so that, just thinking about some of the bottlenecks that we run into when we're doing similar type simulations in non-mem or in Berkeley Madonna, and trying to make it just much more convenient because we've got control over the tool now. And then obviously just interacting with other R functionality, so plotting functionality like ggplot data summary with dplyr and that kind of thing. And there's a lot of simulation that you can do as well in R, that it just kind of working in R, you stay in R, and you can leverage everything that R has to offer. And then obviously you just with these packages, I mean, they're open source, they're free. You don't need a license. Anybody can go download this package and start using it. And we're really trying to stay with our commitment to open source software development and making these tools available to the community. Just a quick note about obtaining mrgsolve. It's open source, it's freely available, but it's not on CRAN. mrgsolve, you can go to our GitHub site here, Metro Research Group /mrgsolve. You can download the R package as source. And so you can get it there. One thing that you might need, or that you do need, that you might not already have on your computer are compilers. So you need a C++ compiler and a Fortran compiler to not only to compile the package, but also to compile your model. And so you might need to do something like install something like rtools.exe on Windows, or install Xcode if you're on Mac with a command line tools, and then a G-Fortran compiler. If you're running on Unix, usually the compilers that you need are already there for you. And we've got a document here, an installation document, installation help here, that'll take you through that process. So what you need, what other packages you need, where to get the compilers, how to install it, and everything you need is available from download from the installation help. And where to get help for with mrgsolve, we've got a user guide up here. I'll link to this and I'll pass this off. So this is a little book that we wrote that will tell you all the syntax that you need to know for creating your models and using mrgsolve. And so that's on our user guide here. Going back to the GitHub site, we've got a wiki where we've got a gallery of worked examples. We've got example models and things like that you can browse, and it might give you ideas for what you want to do with your model. And we've got a slide deck from a workshop that we did out in San Diego last March that takes you kind of from start to finish. That might be helpful. That's in a Beamer slide deck. If you need to report a bug or ask a question, you can do it on GitHub through the issue tracker. Here we've got a Google group that I've linked to here where you can ask a question. Then at least I think related to at least the webinar here, you can ask questions on the thread on the ISOP Discuss site. But hopefully there's plenty of ways to get the questions that you have answered, or that you can get them answered and kind of make progress working with mrgsolve. So just a brief outline for what we're going to do today. So we've only got an hour, so we're not going to be able to go into the type of detail that maybe we'd like to see, but I'd like to just talk a little bit about this mrgsolve model object, and that will help us understand how mrgsolve organizes your model. And it's an R object that you can use to see what's going on in your model a little bit. You can simulate from this model object. So I wanted to show you a little bit about how we work with that. We'll implement some dosing events with an event object, and that's just a quick way to throw a set of dosing interventions at your model to see what's going to happen. Then we'll move into working with data sets. So mrgsolve can take an input in a non-mem-like data set, and that's a way you can either leverage that to either simulate from batches, like doing kind of a sensitivity analysis, or you can think about that as simulating from populations or from like a clinical data set, and that'll show us a little bit how that's working. And then maybe the last half of the session, I'll talk about model specification and show you how you can write your own model. We'll start off with a simple PK model. There'll be some covariates in there. And then we'll expand that to be a PKPD model. And then finally, we'll move in and add some population elements in the model specification. And again, we'll kind of try and gloss over a lot of this, and you can get more of the details especially about the model specification in the user guide. I'm going to be working so I've got an R document called demo.r that I'll pass off to you. And that's basically an R Markdown notebook. And that's going to have all the code that I'm going to hopefully be able to recreate today. And you'll be able to get the code that I type. Hopefully the code that I'll type will look kind of like this, and you can render this into a notebook that'll have the code and the solutions all knit together. I'm going to be, for now, I'm going to be working in this document called worksheet.r that I'll pass off as well. And that's basically that notebook with all the code taken out. And so my job here is to fill in this worksheet and hopefully I'll get a decent grade by the end of the day here. Okay, so that's where we're headed, and hopefully we can get through all this material and give you a flavor for what mrgsolve looks like here. So let's get started. We'll do some preliminaries. We're just loading our libraries. We'll load mrgsolve. I'm going to load this package called mrgmod, and that's just another package that we have up on GitHub, and that is just a library of mrgsolve models that you can load. And initially, we're going to be working with one of the models from that library, and then we'll get to making your own model toward the end of the session here. I'm going to load in some functions here that I don't think we really need, but in case. So we're going to go into mrgmod, and I'm going to load a model object. I'm going to call it PK1 compartment. And we can run that, and we've just kind of loaded this model. It's ready to go. You can get help on this by just going into our help system. And so this is going into mrgmod. It's got a bunch of pharmacokinetic models, and this will tell you some of the details that you might be interested in about what the compartments are, what the parameters are, and things like that, and output variables. But I call this function, and I saved it in this object called mod, and that's kind of my convention whenever I do documentation. And so this mod is just really a mrgsolve model object. And I want to just show you some basics about working with these objects. So there's a show method, so I can just print this to the screen. And this will give us just a basic overview of what's going on with this model. So where the model code came from, so the source is in this file here. We've got information about compartments. So there's 3 compartments in this model. There's a central compartment, then 2 extravascular dosing compartments here. We've got parameters in the model. This will tell us the names, some clearance and volume. We've got a couple absorption rate constants. We've got some nonlinear elimination if we want it. We've got omega and sigma, which are matrices. There's nothing in there right now, but they're matrices for simulating random effects, and we'll get to that when we get to the population piece later on. We've got some solver settings here that you might not need these for a while, but usually once the model starts to get complicated, I'm frequently tweaking the tolerances and maybe the maximum step size here. We saw that we had compartments and parameters here in the model, and we can query what those are. So I've got a function called param, and this will tell us the names and the values of our parameters in the model. So parameters always have some default value assigned to them, and I can check to see what the values are there. And I can do the same thing with a function called init, and that'll tell us the compartments and where they're starting out at. So this is just, they're all starting out at 0, so there's no values in here. But when we do the PKPD model, we'll see where we'll do an indirect response model. We'll see where this value starts off at some non-zero value. So in addition to querying the parameters, so we can take this model object and I can update the parameters here and update the model object, and I can say param, and I can reference one of the parameters there. And I can establish, and this is going to establish a little bit of a pipeline here. We're going to take this model, I'm going to pipe it into the param function. I'm going to change clearance to 333. And I'm going to check the parameters again. That updated that value. And so param not only tells you what the parameters are, like here, it also lets you update the parameters there. And I can also do make a list. And I can not only type in that parameter, but I can add in different R objects to do that update. And so when I updated based on this list here, it's going to look in this list for a clearance item, and it's going to say, oh, it's got to be 222. And now our clearance got updated based on the value in that list. So we can either type in a name and value here, or we can put in a list or a row from a data frame down here and update there. And that's going to be maybe more advanced type modeling work where we're taking maybe samples from a posterior and we want to update our parameters. We can just look at a list or a row in a data frame. Take this model object and I can pass it into a function called mrgsim, and that'll simulate from the model. Here's our simulated output. There's all zeros here because we didn't have any intervention in there. But just taking a quick look at the output, we've got a matrix of simulations here. We've got an ID column. We've got time column. These are always going to be your first two columns. Then we've got all the compartments in the model, the two extravascular and the central. Then I've got the CP column in here, and that is one of my output variables. I can take a look at the model code, and we'll get a little bit into this this later on, but if you go down, there was a capture block, and I captured CP, and that's how the CP got into the output, and CP is plasma concentration. I got it in there because I captured it, and that I captured this global definition, so I defined CP to be the amount in the central compartment divided by VC. And so this is the pattern here. Every time you get every compartment, and then you get all your output variables too. And I can take this and plot it out. So there's a plot method here, and this will give us just a visual look at what happened in our simulation, and nothing happened there. And so let's try and simulate with an events object. So I'm going to add a dosing event, and I'm just going to put amount equals 100 into this first dosing compartment at time 1. And I can take, so again, the workflow here is taking the model object. We're going to modify it with this event. We're going to pass that model object after mrgsim. It's going to do the simulation, and then we're going to plot, and we'll see this over and over again today. So now I've got a single oral dose into the EV1 compartment, and we can see that dose distribute into the central compartment, and we can see the calculated CP there. We can dose into the second compartment. So that'll put the dose into the central compartment, and then now we've got an IV bolus dose here. Or we can also reference this compartment by the name, and this will dose into that second extravascular compartment. So we can do compartment either by number or by name here. Some other things you can have in these EV objects: time, so you can say what time you want the dose to happen. Amount is the dose amount. Rate, if it's a non-zero rate, it'll be a zero order infusion. We can specify the compartment to dose into. We can also specify II and ADDL. II is interdosing interval. And so if we wanted to do once daily dosing, II might be 24 if our model's in hours. And then ADDL are additional doses that we want to give. So just as an example, you can do 300 every 24, and ADDL equals 3. I can switch to the 100 milligram dose every 8 hours for a total of 14. Now the gimmick with these events objects is I can make a composite object out of this. I can say E1, then E2. And now we've got a more complicated event object there, and I can simulate that. So I can simulate from that event object. The simulation didn't really quite come out the way we thought, but I'm just going to adjust the sampling times here. So I'm going to run the simulation out to 240 hours and do a little bit finer time grid. So there, now we got these 4 300 milligram doses followed by every 8 hours, all coming from this events object. And I'm going to just take my model and I'm going to do a update. I'm going to make that persistent. Now, you can see when we simulate from the model, we're by default going out to 240, and we've got this kind of finer grid that we're simulating from. Let's take this. Now we're just going to request different outputs. So we use this request function, and then let's just say I'm only really interested in EV1 and the CP. So I can say I only want that in my output. So now when we simulate from this, actually I can take this out now. We can simulate from this, and now we only get this in our output. And that's not just a plotting trick. We actually only allocated the space in the output for those two columns, and that's what we get. And when we plot, that's what we get on the plot. And I'm just going to do one more persistent update here for the next section. I'm going to end at 96. And we're just going to start only looking at CP. So these are going to, oops. So this update is going to stay with the model. It's going to remember that we're only interested in plasma concentration when we're simulating from now on. And that's just going to help us kind of pare down a little bit what we're looking at in the simulations. In this next section, I just want to go through some data set work with you and show some make some data sets. So I've got a little helper function called expand EV. It's kind of like expand grid, and it's just going to give us all combinations, and we're going to build up this data set where we're going to look at 100, 300, and 1,000 milligram doses. The dose in the compartment 2, we're going to do every 24 hours, and let's just do a bunch of other doses. And then I'm going to do one more make this infusion. 10 hours. Okay, so we built this data set, and let's just take a look. So here we've got, this looks a little bit like that composite events object, but now this is just a plain old data frame. We've got 3 IDs in here. They're all getting different doses, but they're all infusions over 10 hours. And we can take this data set, we can simulate from that by passing in this data set. So I took this model object, we pipe that into this data set function where we identify the data set that we want to use. We simulate with mrgsim and plot, and now we get each individual getting these infusions over 10 hours, and we've got the different dosing in there. But mrg basically, so just what's happening here is that mrgsolve is taking in this data set, it's breaking it up by ID, kind of within this simulation engine. We go into the engine just once, it simulates the whole data set and returns all the simulations once, and we get the whole batch or population, however you want to think about it, simulated in one go here. I can take this, there are some convenience things in here too. I can say ID is greater than 1, and now we only get ID 2 and 3 here. So there's some filtering that you can do here. That's a little bit of a convenience thing. These data sets don't have to be simple like this one. So this is a data set EXTRAN1 that comes with mrgsolve. And so here we've got 5 different people. They've got some people have a 1 record here. 1 and 2, 3 has just a bunch of different records. 5 has something else going on. But basically, the limit here is on the how creative you can get with this data set. So I can simulate EXTRAN1, and this has a little bit of everything going on here. A little bit longer to see what's going on. So again, it'll simulate this batch or population. It's keyed in ID. It does 1 ID at a time, and it just does those interventions, and then gives you the single data set all put back together again. So again, we're using the same model here. We're just varying the data set input to give us the different simulations. One more data set that we've got. I want to just reverse this around a little bit. So we'll do 1,000 milligrams into compartment 2 every 24 hours, and we'll do a bunch of additional doses. Here on my mutate, I'm going to say rate equals amount divided by 10 again. Now I'm going to say clearance equals 0.5 to 2.5 by 0.25. So let's run this. Let's see, what did I go wrong here? Okay. Oh, yeah, sorry, I didn't, that's what here. Better. Let's look at this data set we did here. So now we've got 9 people in the mix. They're all getting the same dose, the same infusion. But now we've got a column in here called clearance. You remember that in our model object, we had a parameter called clearance. And when you do this, mrgsolve will look at this data set and it'll identify this column as one of your parameters. And as it's working through the data set here, it's going to update that value of clearance based on what it finds in your data set. So let me give you a quick look at the results here. Maybe we can simulate this. So now we got all those 9 people with different clearances. They've got the same doses, and we see the variability in the plot or in the population here because we've got different clearances associated with different individuals. So this would be a little bit like a sensitivity analysis that you can do. And it just did this update. So it changed all the clearances for the different people based on what it finds in the data set. And any parameter that you use that you've got in the parameter list, you could conceivably include that in your data frame, and mrgsolve will identify that and it'll do that update as it works through the data set. Yeah, I think that's all I want to say about that. And we can also use a more clinical type data set. This is our beloved Yaflin data set that I've just tweaked to make it kind of compatible with mrgsolve. So this is more like a clinical type data set where we've got doses and we've got observations. And I wanted to just simulate from that, passing that instead into the simulation. And now we can simulate from that data set, and it's a little bit harder to see here, but you can see that the only observations that we get here in the output are the ones that happen in the data set. So if I've got a clinical data set with odd times, I can pass that data set in and I can get simulated values just at those times. And I can also make this another line because to augment this. So when I did this simulation here, it kind of ignored that simulation grid. But I can call this obg function, and that'll take all the times in the Theophylline data set, and it'll augment those times with the times in my simulated time grid. So now I can get all the times in the clinical data set plus this smooth line. And this is really helpful if you're doing things like VPC work. And I can also when I do this, I can get an indicator. Oops, that's the wrong place. Carry out is just say, it's just asking for other things in the output. And usually that's looking for things from the data set. But if I rerun this here, it's run out to the MRD sim. And now I've got a column in the output called aug, and this will be a flag that'll tell me which observations are kind of augmented from that simulation time grid. And those will be ones, and then the zeros are the ones that were actually in the data set. So this 0.25 would have actually been in the data set. So this is really helpful for doing this one simulation. I can pick out the times from my data set, and I can also retain these augmented times here in the simulations. Yeah, so just one more quick thing about carry out. Most of the time what we use is carry out. So in this data set, I've got weight, and I don't think weight really gets involved in the model, but I can carry out anything out of that data set here. Like carry out weight, and this is really what carry out was made to do, is that it looks in your data set, and if it finds this WT column, it actually goes and it actually copies that into your data set. So if you've got a dose group or a covariate level that you want to summarize by, and it's already in your data set, you can just call carry out, and that mrgsolve will just copy that right into your output. You can see in the model, there's weight has nothing to do in the model here, and so there's I don't capture it, I don't identify it as any output, but carry out is a way just to populate that into your output, so you don't have to say like merge against your original data set. You can just carry out the variables that you want to carry forward, either into your plotting facets or into your summarizing variables or things like that. And so carry out is kind of useful for that. I can also carry out amount and EVID. So these are kind of special words that mrgsolve knows how to carry out. And when I carry those things out, I can get an EVID, which is 1 for doses and 0 otherwise, and then it'll give me the amount there as well. And I don't think it had any ADDL. But I can carry that out too, and mrgsolve just knows what ADDL is, and it knows how to carry that into the output. And they're all zeros because ADDL defaulted to 0. So that's kind of a helpful thing that you can use in your simulations. Okay, so that's kind of like the first segment. I think I'm about halfway through, so I'm kind of looking okay on time here. So I think I'm just going to keep going on my worksheet, and we'll get into a little bit of the model specification, things that we can specify in the model. So we'll write out our compartments and our parameters, and we can set initial conditions. We'll see how to do that in the PKPD one. We'll do a little bit of covariate modeling. We'll add some random effects later. We can set things like bioavailability, dosing lag time. We can control the duration or the rate of the infusion there. We'll code some ODEs here, and then we'll specify some variables for output. I'm going to try and just code this first one here. Let's see how fast I can do this. So we're going to code this in line, and so we can either do this in a separate file and read it in, or we can make a little code block here right in R. For bigger projects, I'm almost always writing this into a file because it makes it easier to reuse the code. But for now, just to make it easier, we're going to code it in here, and we're just going to make a file, and we'll read and parse that in a special way that I'll show you in a minute. We'll make some parameters. So we say $param, dvcl equals 1. This will be our little weight on clearance, 0.75. Some compartments, button sent, but that's $CMT. We'll do a covariate model, and we do this in $main. And if you're familiar with non-mem, $main is really like $PK. This is where you get your parameters ready before the system advances. So $main gets called right before the ODEs get solved. So right before the system advances from T1 to T2, we call $main, and we can set up new variables that are used to solve the equations. And so I'm going to derive a new variable here. So if we're writing C++ code in this block, and so I need to type this variable, I'm going to make a variable called CL, and this just says it's a double precision variable. So most of the variables that you're going to derive are going to be doubles. They're just going to be numeric values. And so we just type that by including double on the front here. And then I'm going to say TVCL times POW 70. So we do an exponent in C++. I'm going to say double C. Make this 1 for now. Okay, so there I did a little bit of covariate modeling here. So I did one that illustrates how we derive a new variable. I'm going to make a covariate model, and this model is going to be a function of, I could have some constants in here, but it's going to be a function of other parameters. So I've got a weight in my parameter list that's going to default to 70, and so I can use that symbol in here to fill in this covariate model. Write some ODEs. And I'm going to do a table. This table block is where we identify stuff for output. And I can say table. So this is where I get that CP column divided by V. And then I'm also going to do a capture. And this is for when you already have variables. So I'm going to capture clearance and maybe V in here. Oh, I'm going to capture clearance. That's where you capture, you can insert stuff, items into your simulated output if that variable already exists. So I could capture a parameter value like Ka or something like that. Okay, so this is my model, and let's just load and compile that, and I can create a new model. I'm going to call M code, and I give my model a name, and this is going to be simple. Okay, pass in that code. Oops, let's get this first. This will compile, and nothing bad happened. So it was able to compile, and it loaded that model object, and I got something here to look at. Oops. So just a couple of things about the C++ code. You need a semicolon at the end of every line, and you got to be careful about what you do here with your parameters. So let me just run this and to show you what, in case you run into an error. This is what, when the compile doesn't work, it'll give you an error message saying I expected a semicolon here, but I didn't get it. So let's put that semicolon back there. And then here it's saying undeclared identifier V. Oh, what happened there? Oh, I see. I was using VC instead of V. So let's take that VC back. And then we're going to go back and compile again. Oops. I think I put a on there. In our user guide, I've got a little bit of help in there about working with some of the C++ code. But the key here is identified compartments. In our ODEs, we did a DXDT statement. So that's the differential equation for each compartment in here. What I do here in this $main is kind of completely up to me and how I want to code it. And then we captured some output. So I can take this model now. I'm just gonna change the initial condition for the gut compartment, and I can run that. And now I get something like what we had seen before. So I get all my compartments. I get my output variables, clearance, CP, and Ka. Actually, I'm just going to back off on this. I'm the Ka in there. Okay, so that's that. So now we can I want to just do a quick little sensitivity analysis here. Did I do this ID? So let's just do another data set where we say ID equals 1, amount equals 1,000, apartment is 1, and then and now in my data set, I'm going to say weight. To 140 by 10. So this data set kind of looks like what we had before. Now I've got a covariate here in the column, so it's not a parameter value, but I can pass in this covariate, and let's see what happens here. And it's telling me he simulate log CP versus time by ID. So let's do that. Data. And I'm gonna here. And I wanted to run this out, I think. In there. Here I'll give us a single oral dose, and we've kind of assigned a different weight to everybody, and we can see that the kind of the lowest weight here has a or sorry, the highest weight has the longest half-life, and then that's kind of, you got the reverse relationship for the Cmax. And just to show that what you can do here again with updating a parameter, so we say what happens to half-life. We've got the when we turn that exponent on weight to 1. Remember, we had this kind of fixed to 0.75 here, and we had the exponent on volume to be 1. So let's param. Keep in mind what's going to happen here, what's going to look the half-life. And now everybody's got the same half-life because we've got both clearance and volume scaling with weight in the same relationship. But anyway, that's just a way you can show how we can update one of the parameters here through this param function. And that weight CL is going to apply to everybody. But we did have different weights in the data set here. And then these individual weights will get updated as we work through different individuals in the data set. Okay, let's just copy this, and I'm going to modify. Where do we go? So let's add in KN. So now I'm going to do a PKPD model. So it equals to IC50, 0.5, and I said F. So I'm going to add another parameter called FBio, and that'll be oops, here. Oops. Yep. And that'll be a bioavailability fraction. I'm going to add a response compartment. We're going to say F. Set the bioavailability for the central compartment to be the value F bio. And we're going to set the initial condition. So we see the compartment name resp _0, and that's going to be KN down to like K out. Now we're going to write a differential equation for resp. And I'm going to derive a couple other variables. I'm going to say CP equals cent C. So these will get kind of calculated, and that'll feed into this the indirect response piece here. And we're going to leave the rest of this the same. So the new elements here, I added another compartment. I added some more parameters that we needed for the indirect response model. We set the bioavailability here with F underscore cent, then the compartment name. We initialized this compartment, the response compartment, to be the ratio of K in to K out. And then we added a differential equation there for the response compartment. So let's file that. PKPD. I forgot to put a semicolon there. Let's give it another try. Oh, what did I do here? Oh, I don't need the, I think I had a parentheses there instead of the semicolon. Third time. Oh, yeah, it's V, not VC. This is real life. There you go. So I got the model. So now when I check initial conditions, and we can see this response variable does indeed get initialized to the ratio of K in to K out, and I can do a little, we can update one of the parameters and then call initial conditions on here. And when I change the value of that KN, and that calculated response comes out accordingly. So it's actually calling this code that I have in here when it goes to calculate those initial conditions. Okay, so let's do a quick simulation with this model. Do an IV bolus here. So, so let's do an amount of 100 milligrams to compartment 2. then instead of this, oh yeah, that's what we're doing. Yeah, oh yeah, that's what I'm supposed to do. So let's take this mod. Um, I'm gonna just do this IV bolus times 1. This needs to be compartment equals 2. And then I'm gonna call this knobs function. Knobs function is like an MRG sim, but it's gonna let you do some sensitivity analysis. I'm gonna do a bioavailability from 0 to 1 by 0.1. Let's see how this goes out. When it does this, it's gonna let's just request. Uh, okay, so when it does this, it's gonna tweak this FBio knob. And it's going to change it from 0 to 1 by 0.1. And it's just another way to do a sensitivity analysis here. And we can see what the sensitivity is, that bioavailability parameter on this response piece of this indirect response model here. And then, you could also do K in, do a low, what was K in was 100. Try a couple different KNs here too. Do this. Do the low KN and the high KN. Wait, I think I gotta drop this down actually. I think I wanted to do. Yeah. Anyway, so this knobs is like a tweak the knob. So I can give it the name of a parameter in the model. Here it's FBio KN, and I can give it these different values, and it'll do all those combinations. It'll run the simulation and give you something to plot. So this is just another kind of quick way to do a type of sensitivity analysis in mrgsolve. Okay, we're got just enough time to do the population stuff here. I'm going to copy my code here. Actually, I'm going to copy this. No, I'm going to copy the code. See, our model's getting kind of big. But we're going to add some random effects here. Actually, I'm just going to blow this away. So in mrgsolve, we call these subject level random effects eta 1. We can call it eta 1 and eta 2. Similar if you're familiar with non-mem. So this will give me some between subject variability on clearance and volume. And again, like if you're familiar with non-mem, we can call it $omega block, and we can give these variances. I'm going to do this as a So I'm going to do this as a correlation. I can do the variance of eta 1 is going to be 0.3, and we're going to give it a correlation here, and then the variance of eta 2 is going to be there. I think that's all we needed to do. Let's see if this will get us what we want. Mod. This is pop. So I can say revar on my mod. So we've got an omega matrix. We got one omega matrix in here. We've got the variance of eta 1. We've got the variance of eta 2. And we entered this as a correlation matrix of 0.67, and mrgsolve will go and turn that into a covariance. So mrgsolve always stores this as a full R matrix with covariances and not correlations. But that's just a kind of an easy way to be able to enter that as a correlation. So let's just do a bunch of people here. So we can say odd, make a data set first. Do 50 people here, all 100 kilogram. I think this is just supposed to be just a big data set of people. Data. So we just got a bunch of people, and I want to pass this in as data set. Do this large population simulation. Plotting is going to take longer than the simulating, and then we can get all our simulations here. I think I had V in here too. Let's rerun this. So I'm going to table out that V and run this out again. Okay, so now I've tabled out my clearances, I've tabled out my volumes here. I get the plasma concentration from that single dose, and then I've got the response that came out of that indirect response model. And this just basically shows how, I want to show one more thing here. So I can label these things. And I can, instead of using eta1 and eta2, I can say ECL, substitute these EV. So this just lets us put a little alias on each one of these eta elements. So this will be a 2x2 matrix. So I have to specify two labels here. It'll be eta CL and eta V. And then I can capture these. Instead of ECL, I can capture ECL. EV. Let's recompile this now. Good, it worked. And just rerun our simulation. Now we can get the eta out of there instead of the PK parameter. And so these labels kind of help with the random effects when these matrices get big, and now we're dealing with symbols that kind of make sense to us in our intuitive rather than eta1 and eta2. Okay, so that's just a brief, and obviously we can put covariates in here as well. I think I was supposed to leave a covariate in here, but we can build this covariate model up to be as big as we want with covariates and things like that. You know, we can do something like this. Equals 0. Flag 0 equals b times 2. Makes sense. But we can just do if-else statements. We can do any kind of logic. We can get these parameters set up just so that we want. And the key here is that we've set these parameters up so that they can go into the simulation here, and they influence what the solution is for our differential equations. One other quick thing I wanted to show here is I want to take this same simulation, and we can work with these random effects without recompiling the model. So I'm just going to drop the random effects here. And so before we were getting a plot that looked like that, and I can take the same model, the same data set, I'm going to drop the random effects out of the model. And now we don't get any population variability. You know, those random effects get seeded into zero values. And so this is really, really helpful because we can build up this big population model, maybe with covariates, maybe without, but we can use the same model to just play around with the model. So do typical value simulations, or we can populate that omega matrix with some value that we want to simulate from. And then we can all of a sudden be doing population simulation, but there's no need to go in there and, you know, take out your etas or reconfigure that omega matrix. We have all the control on that in through R here. And there's other things that you can do to that matrix. We can pass in a new matrix through by saying OMAT. That'll we can say DMAT. This might be kind of wild. You can pass in a different matrix there. Yeah, can't do that. So now we're back into population land, and we're simulating from where all the random effects have a variance of 1 here instead of what we populated into the control stream. Whew, okay, so 11 or 12:55, maybe where you are, 11:55 where I am. That's all I had to get through. I'm just going to run quickly here to the question sheet. VJ wants to know, you have ID equals 1 and pass in 3 amounts. Yeah, so that expand, so VJ is asking about this expand EV function. And so this expand EV function will automatically re-ID your data frame so that it's one per row. And it's kind of made to quickly make these one per row type data frames, so one individual per row. But there's no reason why you can't kind of build this up to have multiple different dosing events for each one individual. And I think there might be VJ look into that there might be an option for that to just say make each ID have like the complete a different set of amounts in the doses. But yeah, there's limited kind of ability that we have here on this expand EV to make it complicated. It's really meant to be like an all combinations type of thing. VJ also wants to know, can we simulate from discrete data models? Yeah, so mrgsolve doesn't kind of natively support discrete data right now, so binomial or something like that. But we can compile in our CPP into the model. So, and I think that's going to be coming up in a future release. So we can compile our CPP in, and we can use that to draw from like a beta distribution or a binomial. So you can do that. It's a little bit hacky right now, and I'm hoping to come out with a future version that'll just let you compile an RCPP, and that would give you access to all the different distributions that RCPP, I think it's in that sugar stuff that allows you to simulate from those distributions. Let me see if there's any other questions here. Refresh the screen. Yeah, I don't see any other questions here, but please post on either the ISOP page or on our GitHub site or on the Google group. We'd be happy to help you with a lot of the questions. I know that this was a lot of information here, and that's why we put up the user guide. So please go through that if you want to just read to get more detail, or just feel free to ask us questions. We'd be happy to support your questions and help you answer questions. And we invite you to pull this from GitHub. We invite you to make suggestions about where to go with the package or features that you'd like to see. We really want to keep this open source and kind of community directed as well. So I promised VJ I'd also make one more announcement here. Pharmacometric study group. Our next one is going to be, I think it's a Shiny framework. So we've got the PK. Okay, so we've got two upcoming events here. We've got introduction to the Shiny framework. That check the online. So this says it's coming up on May 20th. Let me see if that's still good. Yep. And then we've got an introduction to a PKNCA. That's Bill Denny's package for doing non-compartmental analysis. That's coming up on May 25th. So please be sure to tune back in and look for this video and the resources that I went through up on the YouTube channel soon. Okay. Thanks everyone for tuning in, and we'll look forward to interacting with you down the road at ACOP or on GitHub.